Hi, it's the future now. Yes, literally about a year since my last upload for Calculus 2. The reason why is because I realized that I don't have any material on areas between curves or volumes, so I'm going to fix that problem now. 1 year later. So 6.1 is about areas between curves. So, it's a really simple concept. Imagine you've just got a couple of curves defined over some interval from A to B. Like this. And you want to find the area of this region right here. Well, there's an easy way to do that. All we have to do is take the area between this upper curve and the x-axis, and the area between this lower curve and the x-axis, and subtract the two. So, above we have f of x, and below we have g of x. What I'm proposing is that we take the definite integral from a to b of f of x, and subtract from that the definite integral from a to b of g of x. Upper minus lower. And that should give us the area of our region. By the way, it is a property of the definite integral that you can split this up so that it becomes f of x minus g of x integral. Right? Hopefully we remember that from the end of Calculus 1. In any case, let's go through some examples of how this works. So, let's say we're going to find the area enclosed by the curves y equals sine x, y equals x, x equals pi over 2, and x equals pi. Whoops. Right then, so if you want to figure out that area, all we've got to do is, again, just take the upper curve minus the lower curve. The question is, which curve is on top? So for that reason, it's often helpful to draw a diagram of the situation. Now, in this example, sine x kind of looks like this, and y equals x kind of looks like this. Okay. Well, actually, I suppose we can do a bit better than that as far as the diagram goes. Something, actually that's a little too wide now. Something kind of like this. So from x equals pi over 2 to x equals pi, that would be from this location up to this location. So we are finding the area of this region right here. Okay. And of course, this upper curve is y equals x, and this lower curve is y equals sine x. So, according to our formula, all we'll have to do is integrate from pi over 2 up to pi, x minus the sine of x. Right, so that's not a particularly hard integral. This just comes out to be 1/2 x squared minus the cosine of x, evaluated from pi over 2 up to pi. Sorry. So, this becomes 1/2 pi squared minus pi over 2 squared minus cosine of pi minus cosine of pi over 2. No, I messed this up. Sorry about that. The antiderivative of negative sine x is positive cosine x. Yes, that makes a difference. There we go. Right, so this is now 1/2 times 3 pi squared over 4 plus cosine of pi is -1, cosine of pi over 2 is 0. And so this just comes out to be 3/8 pi squared minus 1. Lots of different ways to write it, but in any case, that is our answer. Okay? If there's one thing I learned from teaching online, it's that I will never, ever get the lighting right, but nonetheless, I would like to approximate it. Well, in any case, that's all that happens in these examples. You take a couple of curves, and you take their boundaries, you figure out what region you're trying to find the area of, and then you just do that integral. Okay? Let's do another example. So let's say we're just going to try to find the area enclosed by the curves y equals x squared minus 4x and y equals 2x. Now I'm just going to draw a rough sketch of that region. A more detailed sketch is present in my notes. Y equals 2x looks kind of like this. Y equals x squared minus 4x kind of looks like this. So the area we are trying to find looks like this. Right, so area is going to be the integral of the upper curve minus the lower curve. Of course, this upper curve is y equals 2x, and this lower curve is y equals x squared minus 4x. So this just becomes 2x minus x squared minus 4x. Okay, that's great, but what are the bounds? This needs to be a definite integral, right? It can't be an indefinite integral, because an indefinite integral would just return a function, whereas we want an area, which should be a number. So we've got to figure out what the bounds of this region is. We need to figure out the x-coordinates of those 2 points of intersection of these 2 curves. The way you do that is just by setting the 2 equations equal to each other. So we're going to take 2x, and we're going to set that equal to x squared minus 4x. Well, that can be rewritten as 0 equals x squared minus 6x. In other words, 0 equals x times x minus 6. And that gives us 2 solutions, x equals 0 and x equals 6. Well, I guess we should say or x equals 6. Okay, so then what do you think the bounds for the region are? Well, naturally, this one is x equals 0, this one is x equals 6. And so our bounds are just from 0 to 6. So, this just turns into the integral from 0 to 6 of 6x minus x squared. You do the antiderivative, and this becomes, you do the antiderivative, this just becomes 3x squared minus 1/3 x cubed, evaluated from 0 to 6. You put in these numbers, you get 3 times 6 squared minus 0 squared minus 1/3 of 6 cubed minus 0 cubed. How we choose to write it is immaterial. The point is that this comes out to be 36. Okay? Why don't we try another one? This one will be y equals x squared and y equals 4x minus x squared. So once again, in order to get an idea of what the shape of this region is, we should probably draw these 2 curves. And as always, a more precise diagram is found in my notes, but I will just draw a sketch. So here is y equals x squared. And then y equals 4x minus x squared kind of looks like that. So the region that we are trying to find its area is this right here. Once again, they're not telling us the boundaries, and the reason why is because we can figure out the boundaries from the situation. In any case, the upper curve is 4x minus x squared. The lower curve is x squared. So this is going to be the integral from 4x minus x squared, of 4x minus x squared minus x squared. And we're going to have to figure out the bounds. So that means we're going to have to once again figure out the x-coordinates of that point and that point. And once again, the way that we do that is we just set these 2 functions equal to each other. So x squared we're just going to set that equal to 4x minus x squared. That gives us 2x squared minus 4x equals 0, which we can rewrite as 2x times x minus 2 equals 0. And so we have two solutions, x equals 0, x equals 2. So once again, naturally, this point is where x equals 0, and this point is where x equals 2. And so the bounds of our integral are from 0 to 2. So this becomes the integral from 0 to 2, 4x minus 2x squared. You do the antiderivative, and this will just become 2x squared minus 2/3 x cubed, evaluated from 0 to 2. This is then 2 times 2 squared minus 2/3 of 2 cubed minus 2 times 0 squared minus 2/3 of 0 cubed. Again, how we choose to write it is not a big deal, but this is 8, and this is minus 16/3. Yeah. Eight is 24/3, so this altogether comes out to be 8/3. Okay. All right, let's try another one. This one is a little bit different. So this one is x equals y to the 4th, y equals the square root of 2 minus x, and y equals 0. So of course, in order to know what we're looking at, we should probably draw a diagram of this thing. And once again, this will just be a rough sketch, whereas a more detailed sketch can be found in my notes. So y equals x to the 4th kind of looks like this. Y equals the square root of 2 minus x kind of looks like this. And then y equals 0 is just the x-axis. So we're trying to find the area of this region right here. Okay, so if we just sort of blindly apply the formula that we have been using all along, where we just take the integral of the upper minus the lower, then we'll run into a little bit of a problem. We'll run into a little bit of a problem because here, to the left of this dotted line, there is an upper function. To the right of this dotted line, there is a different upper function. So integrating from the floor to the ceiling, well, the ceiling is following a different equation depending on where you are. For this one, it's x equals y to the fourth, but for this one, it's y equals the square root of 2 minus x. Now, you can handle that in one way by just doing two different integrals and adding them together. You can just integrate from floor to ceiling from here over to here, and then from floor to ceiling from here over to here. That'll work. Another way to do this would be to integrate along the y-axis rather than the x-axis, because if we integrate along the y-axis, then we're flipping everything. So our perspective is now like, we're going to integrate from here up to here, and here's our floor, and here's our ceiling. Okay? So rather than going from top to bottom, we're going from leftmost to rightmost. Okay, so suppose we do that. In that case, we're going to have to rewrite this function right here as x as a function of y, which we can do. Y equals square root of 2 minus x gives us y squared equals 2 minus x, in which case x is just 2 minus y squared. All right. So then in that case, what we're going to do is the area is going to be the integral of the ceiling, which is 2 minus y squared, minus the floor, which is y to the fourth. And this is integrating along the y-axis, so we have to have dy. And then the bounds, we need to figure those out too. The lower bound is just y equals 0, because that's where the region starts, y equals 0. The upper bound would be the y-coordinate of this point right here. Again, the way that we find that is we set these two functions equal to each other. So y to the fourth equals 2 minus y squared. That can be rewritten as y to the fourth plus y squared minus 2 equals 0. You can factor that as y squared plus 2, y squared minus 1 equals 0. And then that can be factored as y squared plus 2, y minus 1, y plus 1 equals 0. We get two solutions here, y equals 1 and y equals negative 1. Naturally, this point right here would be where y equals 1, so our integral is going to go from 0 to 1. Okay? So, you do this antiderivative. You get 2y minus 1/3 y cubed minus 1/5 of y to the fifth, evaluated from 0 to 1. That is just 2 times 1 minus 1/3 of 1 cubed minus 1/5 of 1 to the fifth minus 2 times 0 minus 1/3 of 0 cubed minus 1/5 of 0 to the fifth. So, how we choose to write this is unimportant. The fact is, this is a number, which can be represented as 2 minus 1/3 minus 1/5. And let's see, according to my notes, that is just 22/15. Again, how we choose to write this number is unimportant, but the fact that we get this number is all that's important. All right, let's try another one. This one here is y equals x. Y equals x e to the negative x squared. X equals -1. And x equals 1. Let's draw a diagram of this region. As always, a more detailed diagram can be found in my notes, but I'll just produce a sketch. Y equals x e to the negative x squared is a graph that kind of looks like this. Y equals x is a graph that kind of looks like this. And we are trying to find the integral between x equals -1, which would be like right over here, to x equals 1, which would be like right over here. So the region looks like we have this part, but then we also have this other part. Okay? So again, we'd like to just say upper minus lower, but we have a little bit of a problem there, because which one is upper and which one is lower? On the left side of the y-axis, the lower function is y equals x, but on the right side of the y-axis, it's the upper function. Again, just gonna label these really quickly so that we are all on the same page. So which one is on top and which one is on bottom is changing depending on the value of x. All right. Well, that's actually no problem. We can handle that. All you've got to do is figure out the area of this region and the area of this region, and then add them together. So, what we're going to do is the integral from -1 up to 0 of, let's see, upper function is x e to the negative x squared. Lower function is y equals x. Then add to this the integral from 0 up to 1. Y equals x minus y equals x e to the negative x squared. And if we can compute those two integrals, we'll have our answer. So this particular pair of integrals would be most easily handled by just splitting them into 4 integrals. So integral from -1 to 0, x e to the negative x squared, minus integral from -1 to 0, x plus integral from 0 to 1, x minus integral from 0 to 1, x e to the negative x squared. Now, these two integrals are easy. The antiderivative is just 1/2 x squared. These two, first and fourth, need to be done by a u substitution. So u equals -x squared. That forces du to be -2x dx. And the bounds change too. When x equals -1, then u is going to be negative of -1 squared, which is also -1. When x equals 0, u is going to be -0 squared, which is 0. And then over there, when x equals 0, we already agreed that u is going to be 0. When x equals 1, u is going to be -1 squared, so that means u is -1. Okay. So what this comes out to is integral from -1 up to 0 of -1/2 e to the u, then minus integral from -1 up to 0 x, plus integral from 0 up to 1 x, then minus integral from 0 up to -1, -1/2 e to the u, and that would take care of it. Okay, so what we have here is this is just going to be -1/2 e to the u, evaluated from -1 up to 0, minus 1/2 x squared, evaluated from -1 up to 0, plus 1/2 x squared, evaluated from 0 up to 1, plus 1/2 e to the u, evaluated from 0 up to -1. And at this point, I think we're advanced enough that we can figure out the rest of this. The point is that this comes out to be e to the -1 as our answer. Okay. And let's do one more. For this one, we're going to try to find the area enclosed by y equals cosine x, y equals 1 minus cosine x, from x equals 0 to x equals pi. Again, there is a detailed drawing in my notes, but I will just construct a crude diagram of what's going on here. Let's see, y equals cosine x from 0 to pi looks kind of like this. And then y equals 1 minus cosine x, that looks different. That one looks kind of like, here is 2, so then up like that. So this is y equals 1 minus cosine x. This is y equals cosine x. And so we're trying to find the area of this region. Well, once again, they're switching roles. Cosine x is on top here, it's on bottom here. So once again, we're going to have to do two different integrals and then add them together. But in order to do that, we're going to need to know what the x-coordinate of that point right there is. In order to figure that out, we set these two functions equal to each other. Cosine x equals 1 minus cosine x. This becomes 2 cosine x equals 1. In other words, cosine x equals 1/2. And the first positive value at which that occurs is just going to be pi over 3. So, the area is going to be the integral from 0 to pi over 3 of, let's see here, upper minus lower, so that'll be cosine x minus 1 minus cosine x. Then add to this the integral from pi over 3 up to pi. I should label that this is pi. We have 1 minus cosine x minus cosine x. So, this becomes integral from 0 to pi over 3 of, let's see here, 2 cosine x minus 1. Then add to this integral from pi over 3 to pi of 1 minus 2 cosine x. All right. So then this just becomes 2 sine x minus x, evaluated from 0 to pi over 3, plus x minus 2 sine x, evaluated from pi over 3 up to pi. This becomes 2 sine of pi over 3 minus pi over 3 minus 2 sine of 0 minus 0. Add to this pi minus 2 times the sine of pi minus pi over 3 minus 2 times the sine of pi over 3. Sine of pi over 3 is root 3 over 2, so this becomes root 3 minus pi over 3. Sine of 0 is 0, 0 is 0, pi is pi, sine of pi is 0. Then minus pi over 3 plus 2 times sine of pi over 3 is root 3 over 2, so plus root 3. So altogether, this just becomes 2 square root of 3 plus pi, or pi over 3. And that's our answer. All right. So, as always, homework is up. Get some practice with that.